Welcome back. In the last video, I gave you a very quick and rudimentary introduction into what the chemical bond is and what it's composed of. And ultimately, the key idea was that differences in electronegativity do tend to lead to a stronger bond and a bond that will require more energy to break. So we're going to start looking at some molecules to see exactly what happens. Now, within the context of this chapter and this lecture series, when we talk about bond dissociation energies, we're really talking about cleavages in the bond that are homolytic. And that is to say that when you break the bond, you're not producing charged species. All the products are neutral. And the only way that can happen is if by breaking the bond, you give an electron to one of the atoms making up the bond and give the second electron to the opposite atom making up that same bond. So we're going to be looking at the movement of single electrons, which itself is represented by single-headed arrows. So you will not have a double-headed arrow like the one you see here for this reaction, um, but rather you have these single-headed arrows. Notice that here on this particular arrow I'm pointing out, the left portion of it is completely empty or lacking. That's because this is meant to represent the movement of only a single electron. And likewise down here, notice that this curved arrow does not have that double head, only a single head, which tells you that, yeah, you're only moving one electron towards the carbon and you're moving the other electron towards the hydrogen. So in the process of breaking this bond, you are forming what we call radicals. Anytime that you have an element or a molecule that contains a singly unpaired electron, you are dealing with radicals. And much like the common use of the word, being a radical sometimes is not necessarily a good thing. Uh, and that's not to say that radicals in organic chemistry are bad things, but if they are left in check or out of control, they can actually be bad. They can lead to serious problems. Uh, but at the same time, if you can control them and you know how to use them in a small, very controlled setting, that you can actually make good use of radical chemistry. So there are good things about them and bad things about it. But right now, let's focus on what type of bonds we're commonly going to encounter and why they may be stronger than others. And we're going to start with the homonuclear diatomic molecules. In this case, when you do break the bond homolytically, you are going to produce two equivalents of your X dot radical. And a few representative examples are dihydrogen, difluorine, dichlorine, dibromine, and diiodine, right? So simply substitute X for each one of these elements, and you have your corresponding diatomic molecule. Next to it, the second column represents the bond dissociation enthalpy of that diatomic homonuclear molecule. And one thing you're going to notice is that out of the bunch, the hydrogen-hydrogen bond, it is the strongest of the bunch. And if you compare specifically hydrogen to fluorine, the actual discrepancy is huge, right? We're talking about almost 300 kilojoules of mole difference. And the main reason this happens is because the bond length of the hydrogen bond is a lot shorter than that of the fluorine-fluorine bond. Even though we're not going to look into the specifics of this is a direct consequence of the quantum mechanical argument of what the bond represents. In essence, when you have a bond between atoms that have a lower atomic mass, those bonds are stronger. This has to do with something known as the reduced mass, and like I said, it bears its essence from the Schrodinger equation of quantum mechanics. But this is not a physical chemistry class, so we're not going to touch too much on that. But the idea right here is that lighter atoms form stronger bonds. That's one of the key things to keep in mind. So just because the hydrogen-hydrogen bond is smaller than any of the halogen-halogen bonds, automatically makes this a stronger bond and a more difficult bond to break. All right, now with that premise, you would think, well, fluorine is smaller than chlorine, chlorine is smaller than bromine, bromine is smaller than iodine. So you would think there would be a very linear trend from fluorine up to iodine, meaning that the fluorine-fluorine bond should be the strongest one out of the four halogens. But looking at the table, you can clearly see that that's not the case. The fluorine-fluorine bond is in fact the weakest almost out of all the halogens, right? Iodine, the iodine-iodine bond is the only one that beats the fluorine-fluorine bond as being the weaker one. And when you compare the chlorine, bromine, and iodine diatomic molecules, for those three, you do see the actual trend. As this bond length increases for the diatomic molecule, you see a decrease in the bond dissociation enthalpy. That's simply because the bonds are becoming longer. The longer the bonds become, the weaker they are. One way to look at it is that the nuclei are farther away from the electrons of the bond, so the incentive for keeping that bond in there is not as great the longer the bond becomes. Okay, so you may ask at this point, well, what's going on with the fluorine? Why is it that it has a lower bond dissociation enthalpy than the heavier and larger halogens? Well, the reason is that even though the fluorine-fluorine bond is smaller, and in essence that is making the bond stronger, because it is smaller, and because each one of those fluorines has 3 lone pairs, the fact that you're bringing them in really close proximity compared to the other halogens means that you have some serious electron-electron repulsion from adjacent lone pairs. And it's because of this repulsion of the lone pairs that ultimately this bond ends up becoming weaker, even though the size of the bonds makes it stronger. But that completely gets overruled by the fact that you have 3 lone pairs that are literally pushing away from each other. So yeah, that doesn't do you much of a favor. And in essence, this is one of the reasons, among others, for which difluorine is a very dangerous molecule to deal with. It's very reactive. Its bond is very weak, so you can break it apart from radicals, and those radicals can create other bonds that are actually a lot stronger. We'll get to that a little later in this lecture. Okay, so that's the main reason. Now, since we've talked about having shorter bonds and the electron pairs repelling each other on adjacent atoms, it is worth to also bring up oxygen molecules. And this is not dioxygen, but rather peroxide. If you look at hydrogen peroxide, you have a similar situation. Hydrogen peroxide has a relatively short bond, um, relatively similar to that of the fluorine-fluorine bond length. It doesn't have as many lone pairs, right? In fact, one of the lone pairs is substituted by that oxygen-hydrogen bond, but you still have 2 lone pairs, and being in close proximity still creates some steric repulsion. So what you do see is that the bonds of that oxygen-oxygen bond in the peroxide molecule is slightly weaker than that of the chlorine-chlorine bond. So you would expect peroxides to potentially cause problems, and in some situations, yeah, you gotta watch out for them because they can produce radicals and then cause some mayhem if you are a little careless, or you just don't do the proper maintenance of your chemicals, your due diligence. So the hydrogen-hydrogen bond is the strongest, followed by um, technically speaking the chlorine-chlorine bond, which itself is followed by the peroxide oxygen-oxygen bond, and so on and so forth, right? So these are the different explanations that I want you to be aware of. Some of them are based on size, some of them are based on repulsion, some of them are based on electronegativity changes. In the homonuclear atomic molecules, you don't have electronegativity differences because they are the same atoms, right? So even if you were to perform uh, the actual subtraction of electronegativities for these two elements, you will end up with a value of 0 because they are the same elements. All right, so as I pointed out right here, yes, the peroxide oxygen-oxygen bond is weaker than the chlorine bond, which even to me, the first time I noticed that, it was a surprise. Okay, so let's take a look at one more. Let's take a look at the hydrogen X bond. So this is now diatomic molecule, which is heteronuclear. And we're gonna look at the hydrogen halide bonds. We're going to look at some, we're going to also compare it to the hydrogen-hydrogen bond, which was the strongest one in the previous example. And what you see is that once you start mixing and matching the elements, whereas before the fluorine-fluorine bond was one of the weakest, in fact it was almost the weakest one in the list, here the hydrogen-fluorine bond is the strongest of the bunch. And that's closely followed by the hydrogen-oxygen bond right here. It's a semi-close second. Now the reason that's happening is because the hydrogen-fluorine bond creates a really high electronegativity difference. So much so that you have the biggest delta pluses on the H and the biggest delta minuses on your X. That's true for both HF and H2O. So you have relatively strong bonds with those two partners. And they even beat the hydrogen-hydrogen bond, which it is the smallest bond out of everything in here. But that alone is not enough to overtake the huge difference in electronegativities between your hydrogen and fluorine or hydrogen and oxygen. But nonetheless, it is still, a top tier, top tier for the number 3 spot. So it's still a strong bond nonetheless. So don't get me wrong. It is a strong bond to homolytically break. Now after that, you do have your chlorine bond, your HCl bond, which is relatively large. It's not as large as the HF bond because the electronegativity difference is not as great in HCl as it was in HF, right? So you kind of see a relatively linear trend in the electronegativity difference of the two elements and the bond dissociation enthalpy. And when you compare the halogens themselves, fluorine, chlorine, bromine, iodide, since this is now heteronuclear, here you see that trend that we were expecting before, right? The size of the halogen is smaller, making, in the case of fluorine, making a stronger bond, but you also have the electronegativity helping you out, right? So you have higher electronegativity differences and smaller size, making this dissociation enthalpy very large. The bond is stronger. And so going from fluorine to chlorine to bromine to iodine, you see that nice trend of increasing size of the element, decreasing the bond dissociation enthalpy, making the bond weaker. Now, when you compare the bond between hydrogen and another oxygen molecule, so peroxide, the interesting thing about it is that you actually have quite a drop in the bond dissociation enthalpy of the OH bond in peroxide compared to the OH bond in water. And this is not as specifically obvious at first look. And even the first time I saw this, I was very confused by it. So I'm going to try to explain what's going on right here. And the best way to explain it is by spelling out the bonds. So whereas in water, on the opposite side of this HX bond, you have OH. In peroxide, what you have is O bound to another O. And since hydrogen is less electronegative than oxygen, you have electron density being relocated towards the oxygen. So the oxygen develops a greater delta minus in water. In peroxide, however, the oxygen here on the left side is bound to another oxygen. So the electronegativity difference is very small, if any. And so you don't get as much delta minus on this oxygen. And because you don't get enough delta minus, the delta plus of the leftmost hydrogen is not going to be as strongly associated with it, right? So you do lose some of that electron, or not electron, charge to charge interaction. And that's a very subtle point to make, but it is kind of important to realize that going from water to peroxide, you are exchanging a hydrogen for a hydroxy group, right? And it's the hydroxy group that it's changing the electron density map of the oxygen in question that bears the bond that we're about to break. Okay, so that's all about Coulombic attractions and maybe the loss of Coulombic attractions. Okay, now in the next video, what I'm going to start doing is looking at actual organic molecules, because up until this point, everything has been inorganic. So in the next video, let's start looking at those carbon-halogen, carbon-oxygen bonds and see what the picture is for each one of these bond dissociation enthalpies. So see you next.